half-lives. So there are close to 2,000 different nuclei. Approximately 260 are stable and don't decay or change with time. The stability, which means resistance to change, depends on the neutron to proton ratio. Plotting a graph of the number of neutrons versus the number of protons for each element results in a region called the band of stability. So here we have our atomic number, which is the same as the proton number, and on this axis we've got the number of neutrons. So you can see that as we go up, when we have 10 protons and 10 neutrons, it's in the band of stability. When we have 20 neutrons and 20 protons, it's also in the band of stability. For elements with low atomic numbers, below 20, the ratio of neutrons to protons is about 1 to 1. For example, if we have a ratio of 6 neutrons to 6 protons, you divide 6 by 6, and you have 1. So a 1 to 1 ratio. And you'll see that in this band right here. So 1 to 1 ratio is stable when we're talking about elements with low atomic numbers. And a good example of this would be carbon with 6 protons, and 6 neutrons, giving you a mass number of 12. For elements with higher atomic numbers, stable nuclei have more neutrons than protons. The ratio of neutrons to protons is closer to 1.5 for heavier elements. For example, if you have an element that has 82 protons and 24 neutrons, you divide 124 by 82 and you'll come out with about 1.5. And that's where we see this region here in the band of stability. The ratio of neutrons to protons is slightly higher, a few more neutrons than protons, results in stable atoms. Example of this is lead. It has 82 protons and a mass number of 206. The neutron to proton ratio is important because it determines the type of a decay that will occur if an element is unstable. All nuclei that have an atomic number greater than 83 are radioactive and are unstable. Ever wonder why some atomic masses listed on the periodic table have parentheses around them? It's because the atomic masses are estimated due to radioactive decay. These decay usually so quickly that we have to estimate their mass. Half-life. A half-life is defined by the time required for half of the nuclei of a radioactive isotope sample to decay to products. We're going to symbolize this by T, which is time, and then with a half, so subscript of 1/2. For example, if you have 20 atoms of radon-222, the half-life is about 4 days. How many atoms remain at the end of 2 half-lives? So we have time 0, our start time, where we're going to have 20 atoms. We have 1 half-life, our first half-life, and then our second half-life. Well, we start with 20 atoms initially. We go through our first half-life, which takes 4 days to happen. We're going to end with 10 atoms at the end of our first half-life. Another 4 days goes by, which now we're 8 days away from our start time. And we're going to end up with 5 atoms remaining that are still radioactive. So every time the element goes through 1 half-life, only half of the radioactive atoms will remain. We can represent half-life graphically as well. This is an example of carbon-14. If we're thinking at the start, we have 100% of carbon-14. After 1 half-life, each half-life for carbon-14 is 5,730 years. After 1 half-life, we would have 50% of the radioactive element remaining. After the second half-life, we would have 25% of the radioactive element remaining. After the third half-life, we would have 12.5%. And after the fourth half-life, we would have about 6.25 remaining. However, very seldom do we count atoms. Therefore, it's more appropriate to calculate the amount that remains in terms of mass. For example, if you have carbon-14 that emits beta radiation and decays with a half-life of 5,730 years, and we start with a mass of 2.00 times 10 to the negative 12 grams, so this is a tiny amount of carbon-14, we can answer a few different questions. First off, how long is 3 half-lives? Secondly, how many grams of the isotope will remain at the end of the 3 half-lives? So, to calculate the first one, this is actually should be A, we want to know how long 3 half-lives is. Well, each half-life is 5,730 years. So 3 times 5,730 is going to give us our answer. To answer question B, we're going to start with our starting amount, 2.00 times 10 to the negative 12 grams, and then multiply that by half 3 times. So our total number of years that 3 half-lives will take is 17,190 years. At the end of 17,190 years, we will have 2.5 times 10 to the negative 13 grams. 2.00 times 10 to the negative 12 times 1 half times 1 half times 1 half. How many grams of the isotope will remain at the end of 3 half-lives? Here's another way you can do this. Here's 0 times 0. We started with 2.00 times 10 to the negative 12 grams. There's our first half-life. Multiply that number by half. There's our second half-life. Multiply the 1 by half. And there's your answer. Now, we have to go 3 half-lives, so there's our third one. And the amount remaining, after we multiply this by 1 half, is, again, 2.50 times 10 to the negative 13 grams. Each time we go through a half-life, we just multiply it by the starting amount by half. Here's another example. Manganese 56 is a beta emitter with a half-life of 2.6 hours. How many half-lives did the sample go through at the end of 10.4 hours? What's the mass of manganese 56 that's going to be left in a 1 milligram sample of the isotope at the end of the 10.4 hours? So the first calculation we'll need to do is the number of hours that have gone by divided by the half-life. The next calculation, we're going to need to take our 1 milligrams and multiply it by the number of half-lives that this resulted in. So each of them is 2.6 hours. So 10.4 divided by 2.6 will give you 4 half-lives. So to determine the amount of sample that's going to be left at the end of those half-lives, it's 1.0 milligrams times 1 half, times 1 half, times 1 half, times 1 half. Will give you 0.063 milligrams. And that's the end of today. Now we'll practice some problems.